Okay, welcome everyone to the Generative Software Engineering lecture. Today we're going to, last time we were talking about domain-specific languages and mainly the theory behind the different levels of metamodeling. And then we started to look at a framework to actually create these metamodel-based domain-specific languages. And this framework is Xtext, and today we're going to try to apply it to develop a new domain-specific language. Well, not so new, but basically one where we don't have tooling for right now, and then we're trying to get the concrete syntax defined in a grammar, and automatically from that Xtext is going to generate a metamodel. So we're also going to inspect the metamodel that we have created for our modeling language. And then we will also try to do some code generation from that language. Okay, and this somehow captures most of the aspects that we had left in the previous slides. So I think we had almost 20 slides left in the lecture, which were about Xtext and how grammars that you write in Xtext, how they relate to metamodels. So now we're going to do this all on, let's say, practical examples. And the language that we're going to look at is something from the history of computing. It's the Logo language. It's an educational programming language created many years ago. Well, almost, what is this? Like 60, something like 55 years ago, right? And the roots of this language are in artificial intelligence, in mathematical logic, and developmental psychology. So there are different people, I think they were practitioners, but also researchers that started to develop this language. And it was at a time where people just started to develop more high-level programming languages. And indeed, this language Logo has then further influenced many programming languages later on. And if you look a little bit in history, people were, for example, comparing it to things like BASIC, where you wouldn't have methods, you would just jump to specific lines, and that's the time when they introduced Logo, which had some really nice features. But so Logo is a general purpose programming language, and it was intended as such, but it also has a specific syntax. So one part of the language is to basically describe a turtle moving on a canvas and making lines and drawing lines. And we will focus on the turtle aspects of Logo, so we can't quickly in this 1.5 hours develop a full programming language, but we're going to focus on the part where the turtle moves on the canvas. Now, have you ever heard of Logo? No? Okay. So, because there is some, I'm not sure whether it's with a like a ladybird or a turtle, where you have it for educational purposes. So it's a programming language that they teach to children. So it's like really, it goes back many years, but it's still being used today also for teaching programming concepts. But it's not really, and then this mainly focuses on the turtle aspect, so not on the real programming language aspect. And this is so soon after people created this language, it was like the idea of AI and programming robots and things like that. So they also developed a turtle robot. And this is what one of the early turtle robots looks like, which is also something like 50 years or older. Well, it's not a good picture, but maybe there's a better one here maybe. So this was an early turtle robot developed at MIT Artificial Intelligence Lab, and it looks, well, interesting maybe, not the way that robots look like today. Some of the components look very old-fashioned, and there's some video here where you can see it. Let's see, can we actually? Yeah. Do we have sound? Ah, we don't have sound. I'm not even sure that makes sound. So basically that's the turtle robot, and this tail there, I think it's for stability, otherwise it would maybe tip over. And it's also a pen. So the idea is that this thing is really drawing on canvas. So the robot that we're going to try to program with this language today doesn't really have a pen, but the idea is that the moves of the turtle, they would draw some patterns on some canvas, and what you would program is the way that these patterns are drawn. So here, I think it's some, well, we can't really see because the light of this old video is really, really bad, but you might see that it probably draws something on the floor. This line, yeah, that's the pen, right? In the middle there. So that's basically this this turtle robot. Yeah, and there's a lot of stuff about this robot. It was used for different purposes, and this is what the language looks like on the screen. So the actual moves of the turtle, this is what you would program, and the way you would program it is you would say in which direction the turtle should move. So you would have some statement that says forward, and then how many units it should go forward. So forward 50 would basically let the turtle go 50 units forward, and then you have right 45, which is turning the turtle's orientation right by 45 degrees. And then you can go forward again for 25 units. So this way you're basically drawing some stuff. And then, yeah, if you chain enough of these, if you go forward 50, then you turn right 90 degrees, you go forward again 50, you turn right 90 degrees again. You do this whole thing, this sequence, basically 4 times, then the turtle has drawn a square. And yeah, instead of, or in addition to forward, you also have backward, and in addition to right, you also have left. And then it gets a bit more fancy. We also have kind of control structures or stuff like loops and repeats, very basic ones here, but with just using constants, these are some loops that we can create. So we say repeat 4 times the sequence of making this line and then turning 90 degrees right. So that's the same, drawing the same square basically. And this subset of the language is the one we're going to try to implement in a domain-specific language using the Xtext framework. So Xtext is a framework inside Eclipse, and it consists of a bunch of plugins. You have already seen some Xtext languages. So for example, Spectra is an Xtext language, and also the OCL and eCore, I think that's also created using Xtext. So these are some example textual languages. And I'm just going to go back to the slide with the initial command. So we're now trying to set up a language where we can express these, like the forward and the right for now, and then we're going to see how to extend it further. Right. So we can create a new Xtext project. For this, you need to have Xtext installed. I think the modeling Eclipse that everybody installed for the first homework, this has Xtext already installed. And well, of course, the other one, the DSL Eclipse that you installed for the second homework, this also has Xtext installed. So you can basically do it with both. They might have different versions of Xtext. Okay, so yeah, let's define, just going to copy the project name just to make sure that later the packages, they work. Where's my Eclipse? This one, yeah. No, that didn't work. Okay, and then language name should then be turtle language. The extension, let's make it turtle. So then we would edit turtle files. Yeah, and the rest we probably don't have to change anything. We want it to run as an Eclipse plugin. This means it will also give us some editor later so that we can use code completion and stuff for our own DSL. So that's a good thing to have checked. There's also stuff for web integration. Then you can run it in online IDEs. So there are a few online IDEs that that support. I'm not exactly sure if it's the same kind of language server that also Visual Studio Code supports. I'm not 100% sure, but there is integration for that. I didn't try this yet, but yeah. And I think the rest we'll just leave as is. So every Xtext language comes with a few projects. There's one project where the language is defined, and then there are a few additional projects where support for the IDE is provided, where you can write your test cases, and where the UI of the language, the UI contributions of the language can be extended. So these, right now, they don't really have any interesting code. It's just very basic, but if you want to extend how the UI of your language or the UI of the editors works, then you would go into those. Right now, we're mainly focusing on the grammar here, and I'm going to increase it a bit. So that's basically the grammar. We have some name. It already imports some terminal symbols. So this is another grammar. And the reason why they import it is because it's quite useful. It has stuff like ID or integer, and here you see that it's a integer is a terminal in, and we can ignore this stuff for now and have a look at this. So this is a production rule where we can say it's the elements are in the range from 0 to 9, and there are at least one of those. So the plus is the common multiplicity. You can also have the star as multiplicity, then 0 would have been fine. But for an integer, well, it needs at least one digit. Okay, so we're not going to touch this. It's just good to know that it's there, because we will need stuff like integers if we want to say how many steps the turtle should move forward. So we always need one root of the language. So here, this root is called model. We can also call it, maybe, because now we are going to have a programming language, so we can call it program. And then we can define, this is now a production rule, and then we have to define how this rule can be used to create some non-terminals or terminals. So here, this is some existing basic hello world stuff. We don't really need this. What we want to create is, we want to say what's the structure of our turtle programs. So let's go back to the presentation slides. So here we saw the very basic statements, and they can basically be a sequence of statements. So we could simply say that there are some statement, and then how many should we allow? Maybe at least one, right? Program without a statement, not so interesting. And then we should also have, that well, statement is not created. So let's say create the rule statement. And now we can define what a statement could be. So let's take the most simple statement that we had. This was, forward. So we would have the like the terminal value. So now it's not a variable name. This is really just like a string, which means it's really that value. And then we have maybe some integer, right? This would be one of the statements. Now, generator package may not be empty. So there is some issue we didn't yet. So here we have some grammar with production rules. They refer to each other. Now we need to say how actually a meta model can be created from that. And to do that, we can say that the default is that every rule becomes a class. So we would have a class program. And then there are statements in there, right? But now to create a class, we don't know what this statement, where these statements should go. So we could say, well, in the program, there is some field called statements. And this is, if we just say this equals statement, then it would simply be the last statement. So we say here it's plus equals statement. So it collects all the statements that people can write here. So now we have already defined the structure of a program, and we could maybe also have here this integer. What attribute should we associate this with? We could say maybe steps, right? This is a number of steps. And now we don't do plus equals because integer, there's always just a single thing and it needs to be 1. So now let's ask the generator. So what we can do is we can just right click here and say run as generate Xtext artifacts. This would generate the code for this grammar and other stuff. We can also, and what it actually does is defined in this file here. This is a bit confusing. So we didn't touch it so far. And I don't think we even have to touch it because it uses very sensible defaults. So there's, for example, it also generates us a stub for a generator, which is good because we want to later have a generator. But right now, let's just run this workflow here or run the grammar. It doesn't really matter. I think it's doing exactly the same thing in the background. So it's creating some files. It generated a lot of code. And it created here in the model folder an eCore model of our it's a meta model of the domain-specific language that we just created. So let's maybe inspect this. And should I try to wait? Let's create a diagram. It's probably not the best place, but entities in a class diagram for this package. Yep, and here is our meta model. Oh, something is. This is our meta model. We have statement and it's owned by program. So let's maybe program should be then on top. So we have a program and this can have many statements and statements have steps. This is the stuff that we need to store. We don't see anything about forward, right? Because there is only one single kind of statement, and forward is just some part of the concrete syntax, right? Now the question is, would we ever want to change this? So if we, for example, wanted to have forward and backward, then we would need this alternative, and we would have to store it here. So maybe the direction. We could say forward, and to be more, more advanced, let's already put the option backward. Now we have this or in there, this alternative here. That's why we need the parenthesis, because otherwise it would read it as the direction is forward, or we say backward and then some steps. So you have to be aware of the binding of the operators. So the easiest way is to put lots of parentheses. So then there's no confusion about the operators. So the direction can be forward or backward. And then we have steps int. So now let's have a look what happens when we generate the artifacts again. Didn't like that we didn't save the class diagram, right? Critical data, wow. Where did it go? Did we forget to, I guess I forgot to save it. So let's get a new class diagram. Come on, this layout. Okay, so yeah, a program with statements. Now the statements, they have a direction, which is a string, because it stores the constants, and has steps, right? So should we check what kind of languages we can, what kind of models we can create with this? So if we want to see this in action, there is some code generated here. So we need to run an Eclipse that uses this generated code to actually give us an editor for the language. So we would run one of these plugin projects as an Eclipse application. Which always takes some time. And then it should give us an editor where we can actually create programs in our new Turtle language. Not sure what workspace this is going to be. Okay. Okay, that's a Spectra workspace, never mind. So let's create a new project. So now we can just create should be able to create any kind of project. So let's just create a normal project. And let's make it turtle, some turtle tests. And now in this project, let's now create a file, and this file is going to be called, so it needs to be, I don't know, program1.turtle. So now it's important that we get the right extension. Now it detects that, oh, turtle files, they're actually Xtext files. So do you want me to convert the project to an Xtext project? It's just the first time that we have to say yes. And then we see that this file has problems. So let's open the problems view. Here, problems. And let's see what the errors are. So it says, it's not very readable. So it says the required loop did not match anything at input end of file. Basically what it's telling us is that it expects something in this file to be there that is in some loop with a plus. So it needs at least one thing, and we can try to do code completion. Then maybe it will tell us what it wants. So it wants a backward or forward. So let's do a forward. And then save again. And now it tells us mismatched input end of file, where it was expecting the rule int. So now it expects an integer. Code completion says integer 1. Great. So now this one is a valid turtle program. We could even, let's maybe create the turtle program that we have here. The forward 50. That's also valid. And then we had a write 90, which is not going to work because there is nothing for write. So it was expecting, well, that it can't parse further. So it says missing end of file at write. Not the best message to help us, but basically it doesn't understand what write is because we didn't include turns yet, right? So now is a good idea to decide whether we are happy with this kind of meta model where, what do we do is do we push turns in the statement and say, well, direction, forward, backward, right, left might match, right? So let's just call it direction. But then steps, actually it would be degrees, right? So it's not so nice to use the same thing here and maybe, let's say, make steps optional and the degrees optional. So we should probably want to create a new class, which is also a statement, but maybe, special statement. So let's try to separate these statements here. These statements here, they were actually moves, right? So we can call this rule move. And yeah, of course, then we're missing statement. And statement can be either move or turn. And then, of course, we're missing turn. So let's create the rule turn. This will be very similar here. But it will be either right or left. And this one will be something like degrees. So let's see. So the thing is that the meta model will only update once we generate. So we always need to generate the code from this. And this will also update the eCore. So from this grammar, we again generate the code. This might crash our runtime Eclipse. Maybe we should close this for now. Okay, we are putting this in the generated folder. So I think the generated folder is always cleaned by Xtext, but never mind. Okay, now we have a strange layout. So let's put again the program on top. Then what's going on here? Oh. Yeah, okay. So that's the, where did the program go here? That's the new meta model. Is there anything unexpected? Would you have derived this meta model exactly the same from, let me move it side by side, from this grammar? So we see, well, program contains statements, 0 to star, because we have this, well, actually it should be 1 to star, right? Maybe that's added as something like OCL or something. So maybe the meta model is not exactly matching the multiplicities, it looks like. Okay, and then statement can be either move or turn. So it's a kind of parent class for move or turn, which are the subclasses. And then here, actually, we see that it's very kind of clever and identifies that the direction is actually common to both turn and move, and it automatically pulls it up to the parent class. So if they would have had different names, it wouldn't have been able to do that because then they would have been in the subclasses. Okay, so that's our almost exactly corresponding meta model. Now let's have a look. Should we extend it first with loops? Yeah, so let's try to extend it with loops. So we should be able to write something like repeat for, and then in the loop have forward 50 and write 90. So how would we go and extend this with loops? So should we just create something called loop or repeat? Maybe we call it repeat, right? Because we don't really have conditions and stuff. It's just really just a repeat. So what does the repeat need? Needs a keyword, right? We need to start with some keyword where we then know that's now a repeat. So this keyword, what can this be? Must be repeat, right? There's nothing other than so whenever this keyword repeat comes, do we need to make this an attribute of the repeat? So here, it will always ever be repeat. There's no other kind of repeat. So in the other cases, we had the direction which could be forward or backward, and we had to keep track which one we actually chose. But here, we don't need to store this because we know that a repeat is a repeat. So whenever we have an object of class repeat in the metamodel, we know that somewhere in the concrete syntax, it probably was initiated with the keyword repeat. So we don't need to store this keyword repeat. Now, what else do we need? Now we could just write repeat, but that's not enough, right? We need to have, yeah? Some statement. So how should we call this attribute? But it's not really, it's like you said how often. Is how often a good name for an attribute? No. Sorry? Amount? Okay, let's just, yeah. So then, and we make it an attribute so that later, of course, when we process the abstract syntax, we have it available in the metamodel, right? So it's not automatically updating, but yeah. And then you wanted statements, right? How many? So we can copy this from up here, right? Is that going to allow us to write this stuff? No, why not? The block, yeah, these square bracket things, right? So we need those, right? So where would they start? Somewhere here. And then we want to close them somewhere here, right? Okay. So this looks much better. And let's try to generate code from this. Oh, yeah, close this diagram because we have to reinitialize it anyways. Yeah. So actually, if we wouldn't have had these indicators of the block, I think we would have ran into quite some trouble. So I'm not sure if it automatically detects that. Oh, sorry, the statement plus was, we needed that. So let me try to see if it detects that, because the problem is then, if you don't have these square brackets, you could have a repeat, which has, let's say, one statement. And then, because you're in a program, you could have another statement after that. Now, the parser, I think, would not be able to know whether the next statement belongs to the repeat or belongs to the program. And I wonder what, when it probably is fine right now, it might only fall apart if we actually try to parse a corresponding program. Square brackets in and be happy that it doesn't break. Let's put the square brackets in. So yeah, they are really necessary here to distinguish where the statement belongs to. And then, yeah, let's have a look what happens now. We generate this again, and then we create a new diagram. I'll create the diagram somewhere else so that it doesn't always get deleted. Let's have a look. Where's our program? Somewhere down here. Okay. And then we have all kinds of statements. Wait. Oh, this is ugly. These things are... Oh, wait. Our repeat is not a statement. We can't use our repeat. Our repeat has statements, right? But we would not be able to use it. And it is slightly, isn't it gray here? It's not as black as the other ones, right? So basically, we forgot to make our repeat also a statement. We need to say, sorry, not statement is a statement, but repeat is also something that is a statement. Now it looks better. Let's see what, oh no, let's see what happens. Should we, resource has been deleted and contains critic. Oh, again, okay. I guess every time we have to initialize the class diagram again. And then we have our program, which goes to the top. We have our repeat, which now, wait, where does this go? Yep. So now our repeat our repeat now finally is a statement and it contains statements. Good. Yeah, now we should be able to express almost all of these turtle programs, right? So let's run as an Eclipse application and see if we can now write the turtle programs. Maybe I should run it on some more powerful computer and just do desktop sharing or something like that. Okay, so now this is our document, forward right. Let's see if we, if we change something and then save it, it will now revalidate this and it says it's a valid program. So now we said we want a repeat 4 of this program. And we can either put them each in new lines, or put them like this, like it was on the slide. And yeah, this looks like turtle programs, right? We can then maybe even go backward for, I don't know, 100. And then we can turn left for, I don't know, 360, right? Good. So now we have the grammar that defines the concrete syntax. So the grammar defines exactly the keywords that we have repeat, that we have forward, then that afterwards we can use integers, and then we can generate or extract the metamodel from this grammar, where we have compositions and also inheritance. And now how do we actually do anything with this domain-specific language? One thing we might want to do is do code generation, right? So let's pretend this was a turtle robot, and we want this guy to move according to our turtle programs. So where is the... Let me open the Arduino IDE so that we get a reminder of what our programs might look like. So this was the main code initializing all the pins and initializing the motors, and then we had measured some distance and stuff like that, and then we have some code here for using the motors. That's actually... Let's take this one, which is slightly more complicated, but yeah. So we basically have here for every single motor, how do we turn it forward, how do we turn it backward, how do we stop it, stuff like that. So now if we wanted to generate code, we would use maybe existing code like this. So we would start by maybe handcrafting some of the programs that we would later want to generate, right? And then we have here a little bit more complex program, but basically the main structure, we do here the setup of pins, and we initialize all the motors and stuff. That's something that we always need, right? So that's not something that would differ from the generated programs. So we need to identify like what in an example program, what is the constant part that all of the programs will share, and what is the specific part that refers exactly to this one program that the user has written, right? So what is the thing that we really need to change? And usually what you want to do is you want to keep the code generator simple. So you want to keep the part that it generates small. There are different ways to do that. For example, when you generate code for other languages, object-oriented languages, some other languages with options to extract APIs, then you would usually create some kind of runtime environment code, and you would generate code against this runtime environment code. So you don't want to always generate all the technical details. You would encapsulate the technical constant details, the ones that don't change. You would encapsulate them in some API, and then you would generate code that uses that API. So this way you keep the complexity of your code generator low. What we're going to do is we have this kind of constant code here in the beginning, so we could extract some Arduino library maybe, but for us, we'll just say, well, let's take these things as constants, as strings, and always print the string that is the first part of the code, and then do the code that we actually need to generate, and then let's print the string that's the last part of the code. So technically, if we want to create a code generator, we can, the easiest way is to do it the Xtext supported way. So Xtext has support for generating code generators, and it already generated a template for us. So let's have a look at this template. That's the template that it generated for us. And it has some commented out code that's not really going to help us much. But the first part that we need to do is we need to say what file we're going to create by this code generator. So the code generator could be creating many files, can be creating directories, all kinds of things based on one program. So you see the entry point here is a resource. This is the model that we're going to receive. So here it's just resource because it's generic, but that resource is basically the one containing the turtle program. Then we have some file system access object, some API to create files in Eclipse, and then some generator context. So what we want to do here is, I'm just going to copy this from an existing example because, yeah, you can look up the API, but here we're just going to copy these two into our new code generator. So I'm going to copy a different version from this do generate. This do generate now takes the resource contents head, so the first element, as program. Now this program needs to be imported, and that's not sure why it's okay. So this is the one that was generated from the first symbol in our DSL. So that is this thing here, because this is called program. It generates a class program that has these statements. So here we're going to extract this program from the resource that we're getting. Then we derive the Arduino file name. So Arduino code always needs to be in a directory which has the same name as the file name. So somewhere here, the URI last segment, this is going to give us the file name, but it will be treated as the folder because we append this folder thing. Then we get the same append file extension again to the last segment. So we're basically generating files that have the same name as the source file. So if our program was called P1, we're going to generate a folder P1, and then inside we will have a p1.ino. That's the Arduino file extension. So we need to say what files we generate. This is what we're going to do here. And then we need to implement, this method here. That's the one to actually generate the Arduino code. And the one to generate the Arduino code is, quite simple. It's going to print the head of the file. This is a constant that never changes, and print the tail of the file, and then it's going to do some stuff in the middle. But let's first just copy also the head and the tail, because this is just the stuff that we have in our source in our example C program. So here we go. This is the stuff that is like constant all the time. That's how and that's just copied from the bottom of the Arduino code. That's the end of the program. And the beginning of the program always looks like this. Definition of the motor pins, setup of the motors, start of the loop. So in Arduino, we run everything in a loop, but the turtle programs, they don't run in a loop. So here, the workaround is basically at the end, so in the middle, we're going to generate the turtle program. And then at the end, we're going to stop the motors, wait for 5 seconds, and then restart the turtle program, right? So this way, we're still having this kind of loop execution, but we're just, whatever turtle program we generate and upload, we're going to run it in loops. So now, this do generate Arduino code, this is a method that we have created, and we created based on a program. So how do we get the statements of the program? We can have a for loop that loops over all the statements. So we can also use code completion here because we have so program dot, this is our metamodel program now, our abstract syntax. So there we can find the statements, which is a list of statements. So we're going to go over our abstract syntax and then generate the code for each statement. So this generates statement now. We have actually multiple kinds of statements where we want to generate code for, right? So we have turn statements, move statements, and repeat statements. So does anybody know what kind of language this is? Is it Java? It looks a bit like Java, right? But it is. It's another language. It's called Xtend. It's based on Java, but it has some special stuff that's integrated. So, for example, in the kind of methods, you just say def, then you give the return value, the name, and the parameters as you would do in Java. But then here, you actually don't see a return statement in there, right? Because this method is a single statement. So here, the body of this method is only a single statement. It's head plus some other stuff plus tail. So that's a single concatenation of strings. And if a method here only contains a single statement, then the return value of that statement is the return value of the method. So this do generate Arduino code returns a string because head plus some other string plus tail is still a string. So this do generate Arduino code simply returns, well, head plus some stuff we still have to decide and plus tail, right? Now, why did they create their own language? Because that's what they do. They created Xtext, so they also create their own programming languages, right? Actually, the reason is that there are some features here that are quite nice if you handle abstract syntax trees. So if we were using Java, we would have to maybe check now here we have a bunch of statements, right? So we want to have a method that handles statements. Now we could write that method, and then inside that method we could check, is it instance of move, or is it instance of turn, or is it instance of repeat? So here, what this Xtend language allows us is to create different dispatch methods. Dispatch def, and it also returns string, and it is called generate statement, and this thing will only work for move statements. And of course we have to import move. Cannot convert from statement to move. Single dispatch. Okay, let's see what's going to happen if we create some more. So it doesn't like that it's just a single one. We also have the turn. And we also have the repeat, right? So now these kind of dispatch methods, and let's import this. Yep. These dispatch methods, they allow us to handle each case in their own line. So how should we handle moves? What kind of code should we generate for moving? Yeah? So we have these kind of, we can use those methods here in Arduino. So we want to generate Arduino code where it basically says, so whenever we want to generate some kind of template code, we can use these three quotation marks here. So I'll just put this kind of block of code here to give an example. So we want a forward on motor A, forward on motor B. So here we're now mixing the target language concrete syntax with the abstract syntax of the source language. So here, whenever we have like these statements, the for loops or the methods, we are operating on abstract syntax of the source language of the DSL of the turtle programs. And then whenever we put stuff in these three quotation marks, that's actually the stuff to be generated. That is the syntax of the target language. Yeah, how do we make sure that it forwards for some, yeah? You have a question? Exactly. So what do we need from move to know how far? Yeah, that was the step. So let's so now we are in this block where we are, but what does the steps tell us? Do we just call the forward A and forward B I don't know, step number times? The problem is that forward A, they just put some signals on the motors. They return immediately after setting some signals to high or low. So actually to wait for the moving actually to happen, the best thing we do is have a delay. So now if we just wait, let's say we wait for, I don't know, let's say one step is 50 milliseconds, right? But now what you mentioned makes a lot of sense. We actually need some information from the abstract syntax. We need to know how many times 50 milliseconds do we need to wait, or let's make it 100. I have no idea. 50 sounds really short, right? So how many times? Now, what we ideally want to do is we want to maybe multiply this 100 by the steps from the move, right? How do we do that? So actually, there are two ways, because the Arduino language has multiplication. So we could decide, let the target language take care of it. Or we say, well, let's not stress this small microcontroller too much. Let's do the multiplication here while we generate the code. So let's do it while we generate the code, right? Then the poor Arduino doesn't have to do that much work to multiply 100 by some number. So what we now need to do is we need to embed something here that allows us, like some code block that allows us to access the abstract syntax. And there's, of course, some syntax for that. That's these strange brackets there. And there we can have this thing M, which is our move, dot, what was it? Steps, right? Yeah, steps, and let's multiply that by 100, and then let's not have that. And this thing should now put some integer in this delay thing, right? So we are yeah, saving some CPU on the robot, which is good. Now, is this all? Actually, we still need the turn thing, right? The turn thing. Yeah. Yeah. So we probably would have found out that a backward command will now also move forward because it only looks at steps, right? We're never looking at the direction, which is a mistake. So what we probably should do is we might want to add another one of those, have an if statement. So if m dot direction is forward, then we go forward, and then we probably want some else. We go backward, and then we need some and if. So let's check in our Arduino code. I think they were just back. Are they just back? So if we make a mistake here, we're going to generate code that then in Arduino doesn't compile, right? So there's nothing here checking that back A exists. We would only see that after we generated code. So now, hopefully looks better, right? So now we distinguish between backwards and forwards. Should we check whether this works? What? Sorry? Should we stop? I don't know. Yeah, to be safe, maybe. Yeah. Because the language, actually, the turtle language doesn't have a stop, right? So stop A, and this is a method in this kind of C-like syntax. Yeah. Now, I think we should just try to run it to see what's going to happen. So do we still have a runtime running? Yeah. So now we need to, now this code generator actually changed some, can we run this as, should I run it as debug? Well, now I already clicked, okay. I wonder if we run it in debug mode, whether we can do like edit the code generator while we have it generating code. Let's see. So what you can definitely do is you can put breakpoints. So if you get at some point some, you can debug these code generators because they're written in this this kind of DSL here. You want us to debug this, or should we just see whether it works at all? Let's see whether it works at all, because yeah, I'm not sure. Let's have a look, and let's get the robot ready. I hope we can soon upload code. Okay, so first we need to generate the code. The idea of the integration, if we use this template, is that it should automatically, whenever we change the file, it should generate code. Wonder whether we should do some more. Where was it here, right? I'll just create a copy of this program 1 and make it a bit. Let's just have a forward 100 and this. So now let's have a look. In source gen, we find a P1 turtle, which has Arduino code inside. So it generated the folder and then the file. Here we just see the header that we had anyways. And then we see the footer that we had anyways. And here is the code that we generated. Forward A, forward B, delay by, well, 100 times 100, right? And then we stop. see if it compiles. Yeah. Oh, the bottom ones, they are the ones that we had as part of the template. We had them in the, like, this, what I said, because they always run in a loop, we had them like as a stop and then wait for 5 seconds before you run the program again. So these stops here, they are from, the highlighted ones, they are from our, they are from the actual statement. And then the ones below, they are from the template. So this stop and wait 5 seconds before going again. This is in here, the tail. Yeah, we just generated code for a very, very simple program. Is it running? Yeah, it's already reset. So now let's check what happens. We give power to the motors, and then we power up the Arduino, and then it goes forward. It's a bit crooked. And it stopped. So 100 times 100, that's 10 seconds or what? So it should go for 10 seconds, then stop and do the loop. I mean, it's not really going just straight. I think there's some necessary adjustment with this was, no, wait. Why was it doing that? That was not 10 seconds, right? What is the code? Should go forward, then wait 10 seconds, then stop, and wait 5 seconds. Let's start this thing again just to make sure. Okay, so then 5 seconds waiting. Huh. Well, not sure what's going on. Let's generate more code. Okay, maybe I have no idea why it does that. So let's just I'm not sure what's going on, but we had some issues in our code generator, right? There was some, it wasn't really complete. We saw that we were missing some code. For example, the left turn didn't happen at all. So let's go back to our code generator and implement the turn so that we have at least, maybe we could do some sequence of moves. So how would we implement turning? So I'm guessing, I mean, we have again some like direct direction, right? So but now the direction, we're not expecting the direction for turns to be forward. We could say right. Now, should we move both motors forward if we turn right? I'm not 100% sure which one is A and which one is B. So let's say A is the left motor, and if we want to turn right, we should move A forwards and B backwards, right? So let's move A forwards and B backwards. And then for a left turn, we would move A backwards and B forwards. And then steps is not going to work, right? It already tells us here. Steps doesn't exist because we're only 4 turns. What exists is degrees. Degrees times 100, that's maybe a bit... So now we kind of have to guess how many milliseconds does it take to do a full turn? One second? 2 seconds? Let's guess 2 seconds and then just check what happens. So let's say, okay, so the degrees and 360 degrees should be 2 seconds, right? So how do we calculate that? Degrees. We don't have anybody from engineering here. Degrees divided by 360. That's the number of full turns, right? 360, and then we times that by, we said every full turn is 2 seconds. So let's do the degrees times 2000 divided by 360, and yeah, we'll just see what happens. Should we try to do a 360 turn as our next generated code? Now, the question is it, let me close these. Is updating the code generator here enough? We already, we do a, well, let's do a right turn. And let's do a shorter forward of 50, right turn by 360, and then a forward of 50. And it should regenerate our, that's our, wait, which one is this? This is the 1. So let's see, did it regenerate this, or do we need to restart the Eclipse? Okay. This is a bit challenging code, right? So let's maybe, but it's probably fine, right? There was so much code, it must have implemented what we wanted, right? So let's connect the robot and upload this to the robot. It's crazy, this is the CPU usage. Okay. So let's have a look. So now it should go forward, then turn. It's getting stuck in its own cable. Oh, come on. It goes forward, yes. Then it turns, and then it goes forward again. So I think the 2 seconds was a bit too much. So how many turns did it actually do? So we just divide it by 2, which is say 1 second, or? Let's just restart this again. Just, yeah. So that's the forward. It should stop then for a very short time, and then 2. Should we just divide it by? I mean, we're not going to get it accurate to the degree, right? So, or by 1.5, or I don't know. Should we say how many? It didn't really do 2, right? A bit less, almost 2. Let's do 1,200 or something like that. So now that's the forward. That's the turning. What do we do about the repeat? I think now, so I mean, so there are 2 ways to go about this, right? We can say either we want the work to be done by the code generator, and it should expand all the repetitions. It can do that by copying the body many times, right? But you can also nest repeats. So basically just unfolding all of these repeats would be really maybe ugly. So luckily, there's stuff like for loops in the Arduino language. So here I would say we're trying to do a mix. We're not doing all the computation in the code generator. We're going to do the computation partially in the target language and in the code generator. So I would say let's create a for loop. So now in Arduino language, for int I equals 0, I usually less than something, right? And then I plus plus. And then some stuff in the middle, right? So we're missing the comparison for this I. What do we need to compare the I to? Some constant, right? Where does that constant come from? When it says repeat 4 times. This Arduino has no idea about this 4, right? We need to tell, yeah? Yes, so we need to get, it's again in our abstract syntax. So we kind of go back to the level of abstract syntax and say m dot amount. And then what do we need to do in the for loop? What is it that it needs to do in the for loop? There are, M also has some stuff, has a bunch of statements inside, right? What do we need to do with those statements? I would say we need to generate code for these statements, right? Because they are nested inside the repeats, but we still need to generate code for them. So how do we generate code for a bunch of statements? We already had something like that here. That's what we started the program with, right? Because the program has a list of statements and then it needs to generate code for that. Here we basically have, wait, where do we have 2? Okay, here we basically have also a bunch of statements. They're not in program. They are in the abstract syntax of the repeat. And this thing was also called statements, right? So let's have a look. We can have a look in the grammar just to make sure. In the repeat, we have statements. Yeah. And these are the ones that we also want to generate code for. So something like this should do that. So let's open this program that is going to draw a square, right? Let's have a look the generated code. So we can just make sure that it's always freshly generated. We can just delete this, do some small change here, save it, and there it is regenerated. So it regenerates all the modified files. Let's open this. We are expecting to find this for loop. Yeah, and it goes up to 4. That's good. And there's some stuff inside. Good. So let's see if we can put this on the robot and if it's going to drive in a square. Oh, still running some old program. So what are the bets? Is it going to drive in a square? Is it going to fall off the table? I really don't know why these motors are so off. Like, sometimes it's also these cables. If the cables are not correctly attached, then some motor will twist faster than the other, and good. This looks like it's uploaded. Now, I'm just going to put the cable away that it can freely move. Well, good. Let's connect the motors and then wait, this square, it should turn right? So we should start it here. I think it's still going straight. Sorry? No, I think I'm not sure what's going on. Let's check, is the ground thing. I think that one of the motors didn't turn backwards, right? So maybe it's one of those cables. So now it's still going forward. Still going forward. So let's see, did we generate? I don't get it. I mean, we just generated very clear instructions. Let's check. Forward A, forward B for 5 seconds. Then forward and back for 300 milliseconds. And then it goes again. I mean, we don't really need the stops here, because the forward then immediately happens, but I'm not sure whether the stops, I mean, maybe we should have, so there was something about actually voltage spikes. So what happens is if you change the direction of the motors too fast, then there's a spike. of the voltage, and then the Arduino crashes. But I thought this was taken care of by having two separate power supplies, but again, I'm not not an expert there. So the solution or the workaround for that would be to always stop them, wait 500 milliseconds, and then do the next move. So here, to basically put a delay 500 to make sure we're stopping for at least half a second before we turn in other directions. And yeah, for the forward backward, so let's do one last try. This 50 is, wait, what were the constants here? It was driving for 5 seconds. That's a bit much. So should we just have it drive for 1 second, or? I mean, this 90 degrees, this is something where we were hoping that that's kind of accurate, right? So I'm not going to change that now. So let's have a look whether we have new code generated. No, stop. Actually, we could try to run it from the cable. Maybe that's more stable, because then it has the power supply from the laptop. And if there are spikes, then I don't know. Maybe the power bank is not so reliable. I don't know. Let's see what happens. This is our turtle program 2. So this is the last try we have, because then we're out of time. Are there any questions about code generator development in general? It is instantly, isn't it? I think it is instantly. Wait, let me. The slow thing here is the compilation, because that's the C compiler or Arduino compiler. The code generation here is let's see. I think there's a way you can say file preferences. There's somewhere where we can say edit. Is there an edit somewhere? No. Well, let's just. I'm not. I think it's really fast. I'm not sure how we do the refresh. Like if we open this in a text editor instead. I think it's almost instantly. Let's check what happens if we. So now I'm going to save this, and it already rewrote this. So it's really, the code generation is really fast. It's the compilation then that's slow. So generating the metamodel from the grammar. Okay, yes, it does lots of code in the background for the metamodel generation. So it generates this eco model. It makes sure that it has the templates for the generator. So basically, everything that's described in this workflow, it goes through. So yeah, it checks that the Eclipse plugin, I think, is there. It maybe generates, well, no, it doesn't generate a serializer, but checks that the templates are there. So it does actually quite a lot of stuff in the background. And also basically creates a new metamodel in this ecore file. And then we just had to get the class diagram to visualize it, but it already created during the processing. So should we have a look what the program, how it now finally behaves? Let's give it some. Okay, now, and I really hope that the cables are all. Why does it do that? Well, it's almost a square, right? I mean, it kind of does 4 things which are very similar. So let's goes forward, it turns right, goes forward, turns right, goes forward, turns right, goes forward. I think the stop is broken because we call the stop at the end of the loop, we call this stop A and stop B, right? But instead of stopping it, one of the wheels keeps on turning. That's not stop, right? I think there's, yeah. So I think, well, yeah, now we have tons of them open. I don't remember which one was the last one. Was it? No, this one not. Yeah, so are there any questions about this whole process? We basically created our own language. Then we edited some rules for code generation, where basically for every element of the abstract syntax, we have to create some way of translating it to text, and then, yeah, we can get that code generated. So there are different ways you can, instead of generating the code, you could interpret it. So, for example, in Spectra, the code is not generated; the code is translated to some formal game between the environment player and the system player, and then synthesis is done. Doing the parsing and then processing the abstract syntax in some other way. Here we're doing the parsing and then throwing the abstract syntax directly to the code generator. So there are different ways to do that. Yeah. Any questions about this? Then the next session should be on Tuesday, and I think Tuesday I put in there that it's a revision session, so we're going to go over quickly what might be relevant for the exam, and questions that, if you have any questions about any of the materials, maybe it's a good idea to put them in the forum if you can before the revision session, which is very soon. If not, yeah, you can ask them in the revision session. Yeah, because that's then one of the last sessions that we're going to have in this class. So yeah, next session on Tuesday. Okay, see you then.